So on your worksheet, you will need to have a couple of equations. They don't give you any to use. They might give you some in the problem, but they don't give you anything in general. Okay, so for problems that involve growth, you have two to choose from. One of them is y equals a times 1 plus r to the t, and the other one is y equals a times e to the kt. And again, this e is a constant value. It's not a variable. And I'll define all the other variables for you after we write down the decay equations. Decay is y equals a times 1 minus r to the t. So it's really similar to your growth equation. It's just instead of adding the rate, you're subtracting the rate. So instead of having a growth rate, you have a decay rate. And the other one is y equals a times e to the negative kt. And again, e is a constant value. It's not a variable. This negative is part of the equation. So whatever value they give you for k, you're just going to substitute in for the k, and that negative stays in front. Okay, so let's look at number 3 on your worksheet. And we'll work that one out together, and then I can help you get set up on another one if you want me to. Radioactive decay. So just from the title that it has, we know that we're going to be using one of the decay equations. We're going to just have to decide which one to use in here in a minute. Okay, cobalt, an element used to make alloys, has several isotopes. One of these, cobalt-60, is radioactive and has a half-life of 5.7 years. Cobalt-60 is used to trace the path of non-radioactive substances in a system. What is the value of K for cobalt-60? Okay, let me go back and identify the variables. I forgot to do that, I'm sorry. So for all of these equations, the variables stand for the same thing, okay? Y is the amount that the substance grows to or decays. So it grows or decays to that amount. A is your original amount. It's what you have at the very beginning. R is your percentage rate as a decimal. You always want to change a percentage to a decimal when you use it in an equation. T is time. K is a constant number that is specific to the problem that you're working with. So it's going to change, but it's a constant for that problem. Okay, so back to number 3. It's a decay problem. So we're going to use one of these decay equations, and I need to decide which one. So it's asking for the value of K. So the only problem or the only equation that I have that uses K is the second one. So that's the one that I'm going to be using in this problem. So I'm going to write it down here. I'm going to move my paper up. Okay, so I need to identify what the amount is that it decays to, what the initial amount is. K is what I'm going to be solving for. That's an unknown. And then T is the time that it's taken to decay to this Y amount. Well, it says in the problem that this radioactive substance has a half-life of 5.7 years. So I'm going to use 5.7 for the time. That's the time it's given me. Now the initial amount is what it started at. So whenever you first start, you know, it's a whole unit. What percentage would that be? 100. It's 100%. So A as a decimal is going to be 1. So on for Y, at 5.7 years, what does it decay to? How much is left? 50. It's a half-life, yeah. So 0.5. Okay, so now I can substitute values in. 0.5 equals, and since a is 1 and I'm multiplying, it's not really going to change a value anywhere, so I'm not going to put it in there. E to the negative k times 5.7. Okay, so I have my base to the power isolated equals 1/2. So now I want to rewrite it using a logarithm so that I can have it equal to the exponent. Okay, and since it's in base e, I'm going to use natural log. You got ln of 0.5 equals the exponent. So I'm going to type in ln of 0.5, get a value for that, and then divide to solve for k. So ln of 0.5, I'm getting negative 0.69314718006. And they want me to solve for a positive k, right? So what do I need to divide by? Yeah, the negative 5.7. I want to get rid of this negative so that I just have k all by itself. So I'm going to divide negative 5.7, and I'm getting about 0.1216 for k. Any questions? Yes.
Where did you get 0.5 and why?
Because it says in the problem that at 5.7 years it has a half-life. So half-life means half of it's gone. It's decayed down to half. And so that's what it decayed to. Okay, so you guys see one more that you'd like to start?
Are we doing all of them or just?
Yeah, you're going to do all of them on the sheet. But I'll help you get started on one more. One side. Just on the practice side.
Why would it be 0.5 and not 2.5 since that's half of 5.7?
Because 5.7 is the years, and it's talking about half the substance, not half the years. Does that make sense?
Yeah.
Okay. Okay, let's look at number 6. A radioactive element decays exponentially. The decay model is given by the formula A equals A sub 0 times e to the negative 0.04463 t. A is the amount present after t days, and A sub 0 is the amount present initially. Assume you're starting with 50 grams. How much of the element remains after 10 days? After 30 days? So this A sub 0 is 50 grams because that's how much it started with. And then T, they want you to solve when you have 10 days and then when you have 30 days. So you're going to do this twice. You're going to substitute values in. I'll do the one for 10 days and I'll let you guys do the 30-day one. So the decayed amount is 50 times e to the negative 0.04463 times 10. So when you type that into your calculator, the way I'm doing it is I'm going to use this e to the x on your ln button, second ln, and I'm going to use parentheses, negative 0.04463 times 10, close the parentheses. Now I'm using parentheses because I want to keep that all together. And I need to arrow over one so it'll come down off of the exponent and press enter. So I have 0.639991747. Take that times 50 and your decayed amount is 31.999587. So we can round that to about 32. It's 32 grams. That's how much is left.